All right, let's just dive right in. We're about to tackle one of the absolute weirdest, most powerful, and, well, frankly, most reality-bending ideas in all of physics: quantum entanglement. This is a concept that didn't just puzzle scientists, it completely baffled Einstein himself. And today, it's promising to totally reshape our world. So what on earth is this strange cosmic connection?
Here's the game plan. We'll kick things off by unpacking this strange cosmic link. Then, we'll get into why a mind like Einstein's found it so deeply unsettling. After that, we'll see the ultimate test that finally settled a 50-year-long debate. And of course, we'll tackle that huge question: does this thing actually break the speed of light? From there, it's all about the future, the mind-blowing tech this makes possible. And we'll wrap up by asking the biggest question of all: what if reality itself is entangled?
So let's get right to the heart of it. How is it possible for two separate particles, no matter how far apart you pull them, to act like they are a single unified thing? I mean, really think about that. That's the fundamental mystery we've got to unpack. And to really get how bizarre this idea is, you have to start with the guy who gave it its famous nickname, Albert Einstein. He called it spooky action at a distance. And trust me, he was not being complimentary. For him, this whole idea felt like it broke the very rules of the universe that he had helped to write. So what was so spooky to him? Well, here's the definition. It's a quantum state where particles get linked up. And the two keywords you have to focus on here are instantly and no matter the distance. Imagine you have a pair of these particles. One's here on my desk, the other is in the Andromeda galaxy, 2.5 million light years away. The moment I measure a property of my particle, I instantly know the property of its partner. Instantly.
This just isn't how our world works. Take two coins. They're independent objects. If I flip one and get heads, that tells me absolutely nothing about the other coin. But entangled electrons, they are fundamentally different. They don't have their own separate realities. They share a single quantum reality. It's almost like they are two bodies with one quantum soul.
Okay, so let's break down how this actually happens. Before we look, this entangled pair is in a weird haze of every possible outcome, a state we call superposition. It's kind of both spin up and spin down all at once. But the instant we measure just one of them, let's say electron A, the entire shared system just collapses. Poof, all that uncertainty is gone. If A is spin up, then we know right then with 100% certainty that electron B is spin down. And the craziest part? It's not that we discovered its state, it's that our measurement actually created both of their states at the exact same time, across any distance. Now, this instantaneous connection is exactly what bothered Albert Einstein so much. He and his colleagues, Podolsky and Rosen, they put their objections down on paper back in 1935, and that kicked off one of the most important debates in the entire history of science. So let's look at why he was so skeptical. For Einstein, the universe had one absolute unbreakable rule, and it was a rule he came up with. Nothing, and I mean nothing, no objects, no energy, no information can travel faster than the speed of light, period. And this instantaneous action at a distance? It looked like it just completely shattered that cosmic speed limit. How could measuring something here affect something way over there instantly unless some kind of signal was being sent? So to try and fix this, Einstein suggested another idea. He basically said, look, there's no spooky connection at all. These particles must have some kind of hidden variables. Think of it like this. I have a pair of gloves. I put one in one box, the other in a second box, and I mail them to opposite ends of the earth. When you open your box and see a left-handed glove, you instantly know the other one is right-handed. There's no spooky action there. The information was always there. Einstein thought that's how quantum particles must work too. And that set the stage for an incredible showdown. For decades, this was just a philosophical argument. Was the universe spooky, like quantum mechanics said it was? Or was it orderly and predictable, like Einstein's hidden variables suggested? It was time to put reality itself on trial. So the challenge was officially thrown down in 1935. The debate just simmered for almost 30 years until 1964, when a physicist named John Bell came up with a brilliant mathematical test. His theorem was basically a recipe for an experiment, a way you could actually tell the difference between Einstein's hidden gloves and true quantum spookiness. And then, in 1982, a team led by Alain Aspect finally ran the experiment, and they delivered the verdict. And the results were just stunning. See, Bell's theorem predicted that if hidden variables were real, if it was just like the gloves, then the correlations you measure between the particles would have a hard statistical limit. But when Aspect's team ran the experiment, the correlations they found were way, way stronger than Einstein's model could ever explain. The universe wasn't just breaking the limit, it was completely shattering it. It turns out, nature really is that weird.
And this really shows you the brutal honesty of science. The conclusion was just unavoidable. There are no hidden variables. The spooky connection is real. The universe is every bit as strange as quantum mechanics predicted. And in this particular debate, one of the greatest scientific minds in all of human history was simply wrong. Okay, so if this connection is real, and it really is instantaneous, that brings us right back to Einstein's original worry. Are we breaking the speed of light? Could we use this to send messages to Mars with zero time lag? Let's just tackle this thing head on. This is the million-dollar question, isn't it? If I measure my particle and it collapses to spin up, and my friend, millions of light years away, instantly knows their particle is spin down, haven't I just sent them one bit of information, up or down, faster than light? And the answer, which might feel like a total contradiction, is a very firm no. Einstein's theory of relativity, that cosmic speed limit, is perfectly safe. It turns out the universe has a very clever little loophole that keeps everything in order. So why can't we use it to communicate? Well, here's the catch. While the correlation between the particles is instantaneous, the outcome of my measurement is completely random. When I measure my particle, I can't force it to be spin up to send the number 1 or spin down to send a 0. I get what the universe gives me. I have zero control. So yeah, a deep connection exists, but you can't actually steer it to send any kind of useful message. No information is actually transferred. Okay, so if we can't build faster-than-light phones with this stuff, what's the point? Well, this once spooky idea is now moving out of the physics lab and into the real world. And it's becoming the foundation for some of the most revolutionary technologies you can possibly imagine. First on the list, quantum computers. You know, a normal computer bit is either a 0 or a 1. A quantum bit or a qubit can be both at the same time. And when you entangle these qubits, you create this massively interconnected computational space. So instead of checking answers one by one, an entangled system can explore millions of possibilities all at once. This could let us solve problems in medicine or material science that our best supercomputers today wouldn't finish in the entire lifetime of the universe. Next up, security. Quantum entanglement gives us the recipe for truly unbreakable encryption. Imagine sending a secret key using entangled photons. If a spy tries to intercept one of them, the very act of measuring it disturbs the super delicate entangled state. That collapse acts like a cosmic tripwire, instantly telling you that someone's listening in. It's security that's literally guaranteed by the laws of physics. And then you've got the one that sounds like it's straight out of science fiction: quantum teleportation. Now, let's be super clear here. We are not beaming people around like in Star Trek. What's being teleported is information. The complete, exact quantum state of one particle gets transferred onto its distant, entangled partner. The original is actually destroyed in the process, and a perfect copy appears somewhere else. So you're basically teleporting the soul of a particle, not its body. But beyond all the amazing tech, entanglement really forces us to ask some deep questions about the nature of reality itself. This isn't just some quirky feature of tiny particles. It might be a massive clue to the fundamental structure of the entire cosmos. And that leads us to one of the wildest ideas in all of physics today, the ER equals EPR conjecture. So EPR is the entanglement we've been talking about. ER stands for an Einstein-Rosen bridge, which is a wormhole. This theory suggests that every single pair of entangled particles might be physically connected by a tiny microscopic wormhole. The spooky action isn't action at a distance. It's a literal connection right through the fabric of space-time. The ultimate takeaway here is just profound. Entanglement completely challenges our most basic assumption about the world, that it's made of separate things in separate places. It suggests that space-time itself might not be the fundamental backdrop of reality, but something that emerges from all these quantum connections. That at the deepest, most fundamental level, the universe might not be a collection of different parts at all, but a single, deeply interconnected quantum whole. Which really leaves us with a final, pretty unsettling question. If the universe is one giant entangled object, where do you end and where does the rest of it begin?